Good morning, everyone. All right, so we're going back to chapter 4. I had a couple of people ask me to kind of break it down a little bit better, explain it a little bit more. So we're going to go back and really focus on it. So let's first look at that scale. Um, when we're talking about stuff like atoms, and then we're start talking about the structures of metal and the grains and stuff like that, we are talking about stuff that is on an extremely small scale. Um, if you want to think about this, if we looked over to the relative size of various items and stuff like that, this is 1 meter. And this is stuff that you typically measure your chairs in. Also, we get over here to 10 to the negative third power, and we're talking about fleas. And we know how small a flea is, but then we get to 10 to the negative 5 to the negative 4, and that's human hair. And if you're wondering what those negative means, that is 5 zeros, so decimal 1, 2, 3, 4, 5 zeros, and then 10. So that is how small we're getting to. You hear stuff about the nanometers and stuff like that. That's where we're starting to get into stuff like here, nanoparticles, the inorganic compounds and stuff like that. The typical atom diameter is right above 10 to the negative 10th. So I mean, you are getting real small, and that is the full atom. And then we get to the nucleus, which is between negative 15 to negative 14. So we're talking about the size of an atom, and we're talking about how those affect the structure grain, how that affects a compound and stuff. Understand that this is part of an atom that affects what the metal does. So just remember, we are talking about on a humongously small scale that affects literally everything in the universe. We are made of just of those nucleuses, and then those atoms, then the top of compounds, and different particles and stuff. Those tiny itty bitty things make up us. It makes up this metal. It makes up that TV. It makes up the phone that's recording this. So you have to realize we are talking about femtometers compared to millimeters or micrometers, even nanometers. So, for those who've taken your tool class, you have a micrometer and a micrometer. Now, a micrometer is a tool for precise measurement within 1/1000th of an inch. And a micrometer, or a micrometer, or micron, is a unit of measurement 1/millionth of a meter. For those who remember, is that typically when it comes between inches and meters, or imperial versus metric, metric does get you a lot better measurements. That is why it's typically used in the machining trade, because you can get a lot better measurements if it's in the meter, or in the whatever that system is called again. The symbol for it, though, is kind of like this little UM right there. That is what they're talking about when you're using a micrometer. But when you're observing stuff like millimeters, micrometers, and stuff like that, you sometimes have to go get a microscope. Once again, you hear a micrometer and stuff like that, which then you have a microscope kind of telling you on what scale you're trying to look at. If you notice, it says up to 80 times magnification, so that's 80 times more than what our eyes can see visibly. That's how close we get in. Yes, they make ones that are even more precise than that, obviously, because we've seen what atoms look like. But these are for examining extremely small parts or details of a part. But then look at this. This is higher magnification. Just look at the thing right next to it, and you're seeing, 1,500 magnification. That's what that picture is. And those are the marks on a knife. For those who don't, for those who've touched a knife or stuff like that, it's very smooth. It looks crystal clear, looks perfectly good. But when you actually get up there and you're 1,500 times zoomed in, and you notice that we're on the micrometer scale, you see ridges, you see lines and stuff like that. You could almost look at this and be like, oh, that's the bottom of the ocean. Or maybe we're looking at a picture of Mars or something like that. And that's a knife, just really zoomed in. When they're doing stuff like that, the reason why they're typically in black and white is that they're shooting beams of electrons. So part of of an atom, the electrons, protons, and neutrons, and we'll get into those in a second. But they are using that and throwing it out there so they can see what's in there. So we are now in the nanoscale. We are really, really tiny. These are typically used in laboratories and stuff like that to analyze fracture surfaces or stuff like that. Things that, while they might seem like a bad problem to us because it's on a nanoscale, you're not going to be able to see it. Something even on that scale can come back and be a big, big problem. Well, all of this is about the atomic element. The universe is made of elements. The universe is made of atoms, and they're made out of neutrons, protons, and electrons. That is what we're made out of. This is everything. During the Big Bang, all of that was thrown out, and for those who don't know, material cannot be destroyed or changed or anything like that. It just becomes a new, it does change, but it never gets destroyed truthfully. So everything that started off in the beginning is still here. At one time, everything was just the Big Bang, and then it was gases that were out there, and it became stars that exploded, and those became planets. From that stardust, from all that became life, and from life you gain humans. So everything that we're made of, everything that this metal's made out of, this is made out of, was already here. And that's the key thing, is that all of it was here, but it had to be put in a certain order. And once we get to our orders, then you start getting atoms. We go from protons, neutrons, and electrons to atoms, and we go from atoms to getting elements. The big thing to remember is that an atom is the smallest unit of an element that it still has the properties of an element. If I say protons, neutrons, and electrons, those are parts of an atom. But I can change these up and change what the atom is. Especially if I change the neutrons. I can change the electrons and make it positive or negative. So these are things that you have to be aware of when it comes to the element itself. It is the atom that is the smallest unit. If I start taking parts away from the atom, there's no longer properties of that element. So let's look at the structures of an element. You have the nucleus. The nucleus is the center part. Like right here is the nucleus. If we're hydrogen, it's just there. As you can tell, the nucleus has different amounts of protons and neutrons. And the protons are a positively charged piece. The neutrons are neutral. And then the things out here that are surrounding it are your electrons, which are negative. The nucleus is determined, when you're trying to figure out which element it is, it's kind of more determined by the amount of neutrons in it. As you see for hydrogen, it has no protons at all. Magnesium over here has a couple of protons and neutrons, and iron over here has protons and neutrons. And if you're looking at the magnesium, it looks like it has a lot more protons compared to what iron does. Oh, and just as a key note, before we switch to another one, only the outermost electrons influence the behavior of metals. So when we're looking at magnesium, or when we're looking at iron, you see these two electrons on the end? Those are the ones that most affect everything. Those are the ones. Not the ones on the insides and stuff like that. It's these right here, because these are going to be the ones that touch and combine and make our next thing, which are compounds. But when we get to compounds, I'll explain a little bit more and give you a good example. But when we're talking about elements, you've seen the periodic table. This big old thing right here that you've seen in like a million science classes, probably in high school or junior high. Right now it contains 92 naturally occurring elements. So from here to here, those are all natural. All these at the bottom are man-made. Each element has atomic symbols, so such H for hydrogen. So there's your hydrogen right there. You have He for helium, Li for lithium, and stuff like that. So each one has their own symbol. The next one is each element has an atomic number. So, see right here? The atomic number of hydrogen is 1. That's how many neutrons it has. I go over to helium, it has 2. Lithium has 3. Beryllium has 4. And then it just keeps on going, and just scales down. So remember, your neutron setup, which element pretty much it is. Protons and electrons can typically change, especially your electrons. Well, let's talk about compounds. What is a compound? A compound is when you take 2 or more atoms and they come close enough to combine. If you want to think about it, you have hydrogen and you have oxygen. But if I take 2 hydrogen and an oxygen and I put it together, I get H2O. That is the scientific name for water. Water is a compound. The smallest part of water is this compound, which is H2O, and that is the smallest bit of it, which is the molecule. So the molecule is the smallest particle of a compound. It still carries the characteristics of that compound. So if I was looking at the smallest part of water, H2O, that is my smallest molecule. If I take 1 hydrogen away from it, it becomes HO, and it's no longer water. I take the oxygen away from it, now it's just 2 pieces of hydrogen. So it is very particular that when you look at things, the molecule, which is your H2O, is the smallest component, it's the smallest part of that. Now you realize that it's the smallest part of a compound. The smallest part of an element is an atom. The smallest part of a compound is a molecule. So remember that. If you're talking about compound, it's a molecule. If you're talking about an element, it's an atom. And it takes up elements to make a molecule, to make the compound. And remember that, because when we talk about compounds, where it takes 2 or more atoms to come close enough that they make something, steel is a compound. It's technically called an alloy, but it is a compound. So when we're looking at this, remember how we were talking about the outermost electron is the one that matters the most. It is the one that affects how things have properties when it comes to metal. See, these outer electrons came over and actually touched the 2 different atoms, combining and making your molecule. So now they are sharing that electron. So this one probably had 2 electrons, and this one had 1, 2, 3, 4, 5, and now they're sharing the 5 and that one that he had. The force developed between these 2 atoms by sharing an electron is known as a Covalent bond. It's a very strong bond. Some of them are weak, some are easily separated and pulled back apart, some are extremely difficult to take apart. If you kind of look at what steel is, it's really difficult to really take steel back into its base iron and carbon and all that. But stuff like salt water. Salt water is where you puts, let's say it's sodium potassium inside of H2O. You combine it, you make your salt water, and then they'll separate again, and you have salt at the bottom, or stuff like oil and water. You can mix it up where they eventually fuse together, but as you've heard, oil and water don't mix. You can force it to happen. It takes a very strong machine to do it, but after a while, they'll separate back apart. So some are extremely powerful, some are not. So now we're looking at the ionic bonds between atoms, and these bonds are where you start to get into your different structures, and they're starting to bond together and make different things. What you're looking at right now, these are the outermost electron in a sodium atom, which easily transfer to the outermost orbit of a chlorine atom. So, sodium, chlorine, it's moving over. Once it lost that electron, once it lost that one electron, what happened is now it has more protons than it does electrons. And they don't always equal 1 to 1 or something like that. That's not what I'm trying to say. But sometimes what happened is because it lost that negative charge, now it has more of a positive charge, making it positively charged. Just like with this one, because it gained the extra electron, now it's negatively charged. That's why you see the Ci negative in a positive. So letting you know that there's a negative and positive. And things that we know about, like a magnet, like the north and south poles on a magnet, that negative and positive attract each other. So you got negative, positive, negative, positive, negative, positive, negative, positive. These ionic bonds are found in compounds that bond metals to nonmetals. Carbon is a nonmetal. Iron is absolutely a metal. So this is how it happens. Ionic bonds between two atoms when one or more electrons from another are completely transferred to another atom. And that's what we're talking about again, that's positive and negative that keep on switching. Now we're looking at magnetic bond. Metals do not form fixed bounding ratios between atoms. And what they're trying to kind of explain, if you look at it, if you were to kind of think about it, you would think, oh, well, they combine in certain areas, touch really well here and there. But you notice some of these electrons where they're touching and stuff like that, they're kind of spread out. Some of them are way over here, some of them are lapping back around, some of them aren't touching in the right area. And that's because metal doesn't always have that acting property. That's kind of the thing about the metallic bonds. The electrons move between the atomic nuclei and associating equally with all nuclei. Voltage applied to the metal creates electrical current. That's why metals, some of them aren't the best for it, but metals are the ones who are typically your conductors. Some are poor conductors, but they're still conductors. You've probably heard a lot of times, don't be in water when there's an electrical current. And what happens is when lightning actually hits water, if it's pure clean water, it's just H2O, lightning will bounce on top of the water. It won't go anywhere. But why is it dangerous in a bathtub? Well, typically, if you're in a bathtub, you have a drain. What's at the bottom of that drain? A piece of metal. Metals are conductors, so what it does is it goes into the water, and because you're in the water, you've released a little bit of salt in it. Some people accidentally go to the bathroom while they're in a tub or something like that, so now you've increased and made the water pure. You've added materials to it that can be conductors. Remember, a lot of things are classified as metals. So now it has a conductor, and it's going to find the easiest path it can. Which one do you think is easier? Water with a little bit of salt in it, or a human body who has iron in their blood system, who's probably touching that metal drain? Where the easier conductor? And it's going to try to pick the path of least resistance. So that's why it happens. properties depend on the bonding and stuff like that. So when you're looking, you know, over here, you know, we have a milk bottle, or then you have air, you have hard rubber, glass, diamond, which are your non-metals, and you see they're not the greatest of conductivity. Drinking water, like I said, it's not that great. But then all of a sudden you get over here to like graphite, which is carbon. And for those who remember, you know, when you're doing carbon arc is a graphite rod. But we're getting an arc through it to cut out metal. But then we look over here and we start getting into our metals. Stainless steel and mercury are way, you know, they're on the bottom of the list, but they're still a lot better off than something like graphite. Also, we get to our steel, which comes over here, platinum, nickel, zinc, tungsten, which is what we weld with. And then you have gold, copper, and silver, which are our three big ones when it comes to electrical components. That's why when you are, you know, typically running wire for a house, you run copper wire. If you have a cell phone, in your cell phone, they use silver solder on top of gold wire because they're extremely good conductors. That's also why your phones cost so much, because they have gold in them. And as you see, you've probably always heard that gold is the best of all the conductors, and that's not always true. It's just that when it comes to gold, a little piece of gold can be flattened out to like the size of a football field or something like that. I can't remember the exact size, but you can just run gold and it keeps its conductivity very well, even when small, and can handle the heat. Something to think about, and this is very important for those who are going to take aluminum TIG, is that aluminum conducts electricity very well. You can get aluminum wire for electrical components, but aluminum oxide does not. That is the layer that's on top of aluminum. That's why you have to get that oxide off before you TIG weld. Non-metals and compounds with non-metals have certain properties that are all kind of common. They're brittle and they have poor electrical conductivity. A way to kind of think about it is diamond, which is like purified carbon. We've all heard that it's the hardest material or hardest natural material out there. And that's very true. It is like the hardest, one of the absolute hardest. But hard does not mean it's not brittle. We'll start going more into that when we talk about shear strength and stuff like that. But remember, hard typically means it's more brittle. If I took a diamond and I put it on top of this piece of metal and I smacked it with a hammer, the hammer is going to smash that diamond. It will just smash it apart. But if I took that diamond and I went to that glass and I ran down it, I cut the glass with the diamond. So they have different properties and they have different tools or uses if you're going to use them. Typically, if you're drilling, you might use a diamond bit because it is